So maybe the most interesting knot invariant that we're going to study kind of in the beginning here of our tour through knot invariants is going to be what's called a coloration invariant. And a coloration invariant is a way of saying how many different colors I would need to use in order to color the arcs of a diagram for my knot. And let's start with the smallest number of colors for which this is an interesting question. The smallest number is 3. So what we say is a 3 coloring of a knot diagram is a way of assigning to each one of the arcs in my diagram one of 3 distinct colors. Maybe we'll think of them as red, green, and blue. And we call that coloring a valid coloring if every crossing in my colored diagram either is a meeting of 3 arcs having the same color or is a meeting of 3 arcs all of which have different colors. So we'll get some practice with what this means in a minute. But if I have a knot diagram that has a valid 3 coloring, if there is a way for me to use 3 colors to color in the arcs of my diagrams such that all 3 are the same color or all 3 are different colors at each crossing on my diagram, then we call that diagram tricolorable. And the only other thing we have to insist upon is that we are actually using all 3 colors. We can't just color the whole diagram green, because that would pass my test, because all the arcs at every crossing would be the same color, but it wouldn't be very interesting because every diagram can be colored with all the same color and pass that test. So it's only really interesting if there exists a coloring that uses all 3 colors and at which passes the validity test for 3 coloration. So here's what we're talking about. If I start with a diagram of the trefoil, so here's a diagram of our trefoil knot. It's got 3 arcs and 3 crossings. If I color all of the arcs the same color, then we would say that this is a valid 3 coloration, right? Because every crossing is a crossing where 3 arcs all have the same color, because all 3 of them have red. Right? All 3 of the arc pieces that are coming into my crossings have the same color at each diagram. But if I change the color on one of my arcs, let's say I recolor that one green. Right? Now this crossing is invalid because there exists a crossing at which it's neither the case that all 3 arcs at that crossing have the same color, nor the case that all 3 arcs at that crossing have different colors. Right? So this would be invalid because 2 of the arcs at this crossing have the same color as one another, but the 3rd arc has a different color. So we only have a valid coloration if we can color it in such a way, and now we have a valid coloration again, that at every crossing, either it's the case that 3 arcs of the same color are coming together, or that 3 arcs of all different colors are coming together. And now this is a valid 3 coloration that's non-trivial. This is an interesting 3 coloration for this knot, because we're using all 3 colors, red, green, and blue, and it's also the case that all of the crossings have the property that either all the colors are the same, or all the colors are different at each crossing. In this example, we see all 3 colors coming into each crossing are different from one another. So this is a valid and non-trivial 3 coloration for the trefoil. And so it's a valid question to ask whether coloration is telling me something just about the diagrams of knots, or whether the coloration is telling me something about the knots themselves. Is coloration actually a knot invariant? So to see whether or not tricolorability is a knot invariant, let's imagine once again that I have some tricolorable knot. Say that I have the ability to tricolor this particular diagram. Question is, if I apply a type 1 Rydermeister move, can I still tricolor this diagram? So is this diagram tricolorable, given that my original diagram was tricolorable? So the only question is, what happens with this new crossing? Is there a way for me to assign colors to this diagram that respects the new crossing that's here? So to figure that out, let's just imagine that originally I had colored this arc with a color. Let's say we originally colored it red. If I do that Rydermeister twist, am I still going to have a valid coloration? Because we've created a new crossing, and so this is a new place for the validity test for tricolorability to potentially fail. Remember, a coloration is valid if at every crossing all 3 arcs either have the same color or all 3 arcs of that crossing have 3 different colors. Can I finish a coloration of this diagram that gives me a valid coloration at this new crossing? knowing that all the rest of the crossings in my diagram already have validity to them because we assumed that the original diagram was tricolorable. So how could I color this part of the diagram in a valid way at this crossing? Well, we only still have a single arc here, right? Adding in this new twist, we know that this piece, this new piece of the arc, I'm going to try and color a little bit more vividly here. This new piece of the arc has to have the same color as the piece that it was connected to, and that piece already had a red color, so this piece has to have a red color as well. But the same is true of this little piece of arc over here as well, because it's connected to the arc that we also had originally colored red. So the only way that we can color this crossing is just to color the whole thing red. But that's valid, right? It's valid to have all three colors be the same at a crossing. So if my original knot was tricolorable, then I know that my new knot, after I did my type 1 Rydermeister move, will still be tricolorable. I just keep the same color on whatever arc it is that I'm putting a twist in, right? And my old valid coloration becomes a new valid coloration after the type 1 Rydermeister move is done. All right, so how about the type 2 move? So we have some nasty looking knot diagram, and we have a little piece of the diagram that looks like this. My original diagram is tricolorable, so whatever color this string originally had in my valid tricoloration, I'm just going to kind of draw it in there as though it's red. Now let's perform a type 2 Rydermeister move. Type 2 is just going to pull the sheep's head out and under and do this poke maneuver. So the question is, can I color this diagram in a valid way? Well, just based on what these arcs are connected to, I'm sort of stuck with coloring this piece red and coloring that piece red. So that's got to be red. That's got to be red. So the only question I have now is, what color can I assign to this little piece over here? Can I assign it any color that makes this a valid coloration? But I look at these two crossings and say, at each of these crossings, I have two incident arcs that are both colored the same, right? This over crossing and this little under arc here are both red. And so in order to make a valid coloration, I would have to have this piece over here have the same color as those two. So that piece would have to be red as well. And the same is true at this crossing. Two of the incident arcs are red, so the other one has to be red as well. So my hand is sort of forced. But the good news is, after my hand is forced, I've colored these two pieces red and they connect to one another, and so it's okay to color that whole arc red and get a valid coloration. So if I had a valid coloration before I did this poking maneuver, I will still have a valid coloration after I've done the poking maneuver just by keeping the same color on that new little piece of poked arc that we put underneath the previous one. So we passed the type 2 test for tricolorability. How about type 3? Well, for type 3, I'm actually just going to go back to the diagram from our text of what that type 3 Rydermeister move actually looks like. So here it is. Let's suppose that I had a crossing at which I have a couple of different colors coming together, and then my third string has a different color still, so a red, a green, and a blue. If I had a valid tricoloration on the left side of this diagram, I'm going to have a valid tricoloration on the right side of this diagram as well. Actually, it's not the greatest diagram to use, because actually this green-blue crossing here is not a valid crossing for the purposes of tricoloration, because we have two colors that are the same, the blue and the blue, but the third color, the green, is different. So maybe I do need to make my own diagram for this. So I have some nasty piece of diagram over here. I have, I'm creating a crossing here somewhere. And so I'm going to imagine that, maybe I have a green strand coming over. Maybe I have a blue strand coming out of it this way, going back into my diagram somewhere. And then additionally, I also have some red strand coming out and passing underneath both of those. And maybe this goes back into the diagram somewhere. Maybe this goes back into the diagram somewhere. Maybe this goes back into the diagram somewhere, right? So we're just sort of zooming in on a piece of this diagram where we're hoping to see some kind of coloration effect, right? Well, here's the thing. If I have two different colors at this crossing, it must mean that the third color that I have at that crossing is different than the first two. That's the only way to have a valid tricoloration in the first place. So if I have a green and a blue at this crossing, I also have to have a red. The same is true at this crossing. If I have a green and a red, this one has to be blue. But if that one's blue, then that blue is going to intersect with this blue over here, which we can't have unless we colored all of it blue. So, all right, so maybe we'll do that. Maybe that's okay. So if this is blue, then that forces this piece to be blue. Anyway, so the question, actually, I kind of want to do this differently, right? I kind of want the strand that I'm moving in my type 3 move, this one over here, I want it to maybe all have the same color. So let me back up a tinge here. And just kind of imagine, once again, that I have this under arc that's sort of crossing back into here. This is going back into the diagram somewhere. That goes back into the diagram somewhere. And so I have this red strand that's passing underneath. Oh, but I can't do that, can I? Because that's going to, again, if this red and this green are different, it's going to force them all to be red at this part of the diagram. This is what happens when I'm over time and I start to talk myself in circles. I'm just going to punt on this one for right now and say that there is a diagram that shows that this does work with a type 3 maneuver, and I'm just having trouble pulling it out of thin air at the moment. It's something that looks sort of very similar to this diagram, but you need to kind of consider a variety of different cases, like what are the colors of the various arcs that are a part of this diagram, because it turns out there start to be a lot of arcs when we draw this diagram in there. But we can show that whether or not a diagram can be 3-colored, whether a tricoloration that's non-trivial exists, is something that's preserved by all 3 of these Rydermeister moves, and therefore it is a knot invariant. So what that means is that I can tell knots apart by telling whether or not they are tricolorable. So here's an example of a knot diagram, and I can kind of see if I can make a non-trivial tricoloration for it by changing the colors of some of the arcs on this diagram. So if these two are both red, then this third one would have to be red. But if I want different colors, then I would force one of these to be blue. Now this crossing is valid up here at the top because all 3 are different. This crossing over here is valid because all 3 are different. This crossing over here is not valid anymore because I have 2 blues, but not a third blue. So in order to try to make it valid, we would have to turn one of these blues into a green. But if I turn this blue into a green, it's going to have a problem with the arc over there. And if I turn this blue into a green, it's going to have a problem with the arc over there. And so if you play around with this diagram, you'll eventually figure out that there is no way for us to assign colors to the arcs of this diagram using all 3 of red, green, and blue in a way that gives me a valid coloration. And so what does that tell me about this knot? It tells me that this knot is definitely different than that one, right? Because if we believe that tricolorability is a knot invariant, that means that every diagram of the trefoil will either all be tricolorable or they'll all be not tricolorable. Right? And here is an example of a diagram of the trefoil that is tricolorable. Therefore, if this is a diagram that's not tricolorable, then it can't be a diagram of the trefoil. So this is how we can use knot invariants to at least tell me what a diagram is not. What knot a diagram does not represent, right? Because as soon as I find a disagreement on a property between 2 diagrams on a knot invariant, then that disagreement is a real disagreement between knots and not just a difference between their diagrams. Using colors to color the arcs of a diagram subject to these diagram rules, these coloration rules, is going to be our way next week of sort of laddering ourselves up to these higher algebraic invariants for knots that get much more interesting and much more complex. But it's all going to begin with taking out crayons and trying to color the arcs on a knot diagram subject to these 3 coloration rules.